So, now that I start stream, just to reiterate something I just mentioned. The free response grades I'll have in by tomorrow. They're technically done, I guess, but they're just not all in the file that I sent, so I just need to wait on that, and I should get them from the grader tomorrow as well. So, yay, that'll all be in there. People did well. I mean, again, I also mentioned this just a couple minutes ago in class. One of the questions was, in my opinion, pretty easy. One of the questions is basically 2 multiple choice questions that I could have asked in terms of the amount of time it took or something like that. So anywho, all that to say, the scores looked good. I posted, if you all saw the announcement I sent out yesterday, the Learning Assistant application. So this is for the fall. Learning Assistants, you're not going to be as familiar with them as my other class. Learning Assistants work in the studio class. So the studio class is the other class I teach, which is this. You probably pass by the room if you walk. So it's on the 3rd floor. It's room 350. It's the room that's got a bunch of circle tables in it. You peek through the window. It's a big room with a bunch of circle tables with computers and stuff like that. So the studio class, think of it more like a high school environment. And I say that not to mean like difficulty, but I mean you're in tables together with other people. There is actually enough time for us to go around and actually work with people in the class. So they're in the studio class, there's myself, there's a graduate teaching assistant, and then there's an undergraduate learning assistant. And so the class meets 2 days a week for 2 hours and 50 minutes, which would be like, oh my gosh, so much time. It's the recitation, the class, and the lab all together though. So if you all took the time that you spent in this class plus the recitation plus the lab, it's the same amount of time. So it works out the same. Anyway, as a learning assistant, you basically help students. Think of it like a tutor. So you're in the room with me during the class, and like whenever you all have seen me solve problems in here, instead of me just waiting 30 seconds or a minute, I give many minutes. If you're watching my streams on it, 5 minutes, 10 minutes, and we're going around the room and actually helping people solve the problems. So learning assistant, you work in the classroom with students to help them solve things. And then you hold a couple, let's call them office hours. They're called help room hours. If you've gone to the help room, those are the learning assistants. And you work with people that come on in and you help them solve stuff. It is, in my opinion, all the best parts about teaching. And I'm biased. It's all human interaction. You don't do any grading. You don't do any lesson planning or anything like that, though you could work with your instructor to help with that if that's something you were interested in. But yeah, it's a really fun thing. I was a learning assistant when I did my undergrad here. It's actually what showed me I wanted to be a teacher. I knew I wanted to teach at some point, but doing this showed me that, oh man, this is a lot of fun. I enjoyed it a lot. So all that to say, they don't hire a ton. We get maybe 10 or something like that positions. Its competitiveness is based upon how well it's advertised, honestly. The more people it's advertised to, the more they have. Generally, what often ends up being the bottleneck is what works with people's schedules, because again, you're in the studio room during those class times, so your schedule has to work for that. Anyway, one day this flyer will load. It has the details on it. Yay, look, there it is. Basically, if you are currently doing excellent in this class, really well, stuff's coming naturally to you, totally makes sense. It says earn a B or higher. I layered that to an A or higher, in my opinion. So these are the minimum requirements, but honestly, A or higher is kind of what I would think of. And you think you're interested in teaching at some point, highly recommend this. It's a great opportunity. You'll learn the physics so well. The best way to learn something is to teach it, as weird as that sounds. You find that when you have to explain something to someone, you have to answer questions in your own head that you haven't maybe answered before. You'll experience it at some point in your life. There's one little caveat to this position, and it's that if you sign up for this position, and it's in this thing when you apply for it, so it's not on the flyer, it's in the application. You do have to sign up for this 1 hour pedagogy course, and if you haven't heard the word pedagogy is a fancy word which is basically how to teach. Pedagogy is how to teach. And teaching is not just telling people a bunch of information. In fact, effective teaching, as weird as it sounds, is not what I do in this room. because there's too many of you all, honestly, to do the most effective thing. So what you learn in this is how to actually be an effective teacher, which means you go around and, because you're working with students, guided inquiry is a thing. No one really likes guided. People tend to not like it, but it is the best way to learn. Guided inquiry is the thing that when you go up to someone, you ask them a question, they ask you a question back. People tend to not like it, but it is the best way to learn. Sometimes they just give the answer, but a lot of things, if you come to my office hours, you've experienced this. When you're working through a problem and you say, I'm stumped here, I'll ask you a question, like, what are we solving for, or what's going on here, or, and those leading questions are to kind of train you to ask yourself the right questions, because so much of life is just learning to ask yourself the right questions, and at some point it becomes natural. Anyway, all that to say, this course is really, really, really useful. Teaching is not trivial. Teaching is trivial. Being a good teacher is not trivial. So.
Do you have multiple studio classes?
There are multiple studio classes. I only teach one of them.
So if you were if you wanted to complete the 10 hours, you would have to do one class per day, right?
Yeah. So if you get this position, the way it works is you're assigned to one studio class. So one studio class means 2 days a week, 6 hours. Whether that's Tuesday, Thursday, 2 hours and 50 minutes each day, or whether it's Monday, Wednesday, Friday, 1 hour and 50 minutes each day. So that's 6 hours, plus you have the 2 hours for doing the help room. That gets you to 8. And then the other 2 hours are just kind of like preparing and miscellaneous things. Those get filled really easily. Yeah. The studio classes meet for twice as long as like a lecture class. But again, for your own kind of thing, if you're thinking of ever taking a studio class, it includes the recitation, it includes the lab. So it's actually the same amount of in-person hours as for you all. If you added up the class time plus recitation plus lab, it equals about 6 hours a week. So, anyway, yeah, if you have any questions about it, let me know. Great thing. Loved it personally. Had a great time as it. And there's also at some point Sark will open their hiring. I know nothing about their hiring process. Sure. This is the announcement. Yeah, I can put it up again. Yeah. I can put it very briefly, but this is the announcement I sent out with this. So, yeah.
Do you have to be a physics undergrad student?
You do not need to be a physics undergrad student. Nope. You don't need to be an engineering major. In fact, I think there's a lot of benefit to health science majors being LAs, because if you're paired with a health science, course, so if you could get paired with a 2053 person, and you're gonna have a better sense of what it's like to take a physics class as a health science major compared to engineering students. If you're with a 2053, you're gonna know the experience of a health science major in a physics class better, because many of you are health science majors in a physics class. So there's some benefit there. Kind of, sorta. Generally, they'll put you with the one that you can fit in schedule-wise. So with some constraints, they might say hey, your schedule is there's an interview, there's this application and interview process, and then if they say yay, they tend to say, okay, here's the ones that fit, and that you may or may not get it. I honestly don't know for sure. But obviously it has to fit within your schedule. That's the most important thing. That's often what prevents a lot of people from being able to do the position, is if they just can't fit within the classes that are available. Because hopefully this is probably obvious. You probably can't be in LA for a Physics 2 class, because you haven't taught Physics 2. Yeah. So you would get assigned to Physics 1 class. Maybe 2053, there's a chance they could put you in 2048, but again, that requires some calculus, which you wouldn't be able to help with, which is a bummer. So I don't know. Yeah. But anyway, there's a few Studio 2053 classes, 2 or 3 of them or something. So cool. All right. Last class, we talked about torque. So torque was the force version of it's the rotational version of force. So if there's a torque, things angular accelerate. Just like if there's a force, things accelerate. All right? So where there's a force, where there's a net force, there's an acceleration. Where there's a net torque, there's an angular acceleration. And the way you apply a torque was that Fr sine theta. That was in the other things. You all, basically the question is, how do you make something start spinning? You apply a force on it. If you apply a force this way to the right, on the right side of a circle, it's not going to spin. Why is it not going to spin? Because the radius vector is the same direction and it's not going to spin. You all know this. Hopefully you've tried to spin things. So how do I make it spin? If I want to make it spin the most, I apply a force perpendicular, tangent to the surface. 90 degrees to the radius. Again, you all know this. You want to make something spin on the right side of it, you're going to push it down. Why? Because the angle is 90 degrees, you get a net torque. Torque equals RF sine theta. And to give you all another connection of this, so great, angle matters, force hopefully obviously matters. The radius, so the farther away from the axis of rotation you push, the easier it is to angular accelerate. And the first question I asked you all is how do you loosen a bolt? Long wrench or short wrench? The answer is long wrench. Why? You get more torque. Another very easy example I forgot to mention to you all is literally opening a door. When you open a door, you don't push near the hinge. No one pushes it. That's really hard to open a door. Here's a door in this corner. You totally can't see it. I will draw a door. It will be beautiful. Look, this thing in front of me is a door. Great, this is a door. This is the hinge. It's attached to the wall. No one's trying to open a door by pushing near the hinge. Why? It's really hard to open a door if you push near the hinge. Why again? Because the torque is really small. R is really small, so torque is really small. It's hard to open. So where do you push? Really far away. And wow, it's so easy to spin the desk now. Open the door. Because your torque is larger. So you all have lots of experience with this, whether or not you realize it. Okay. The main thing I need to teach you all in this entire PowerPoint is this fancy phrase called moment of inertia. We're going to need that. I keep telling you torque is connected to angular acceleration. How it's connected, instead of F equals ma. So, what's the relationship between force and acceleration? F equals ma. More mass, less acceleration. Hopefully we're cool with that. The thing I'm going to teach you all is that torque is going to be like the same thing, but instead of m, we're going to have this letter I. That's going to be kind of like the new thing. In this entire PowerPoint, in my opinion, I is like the only new thing. Everything else is just going to be putting equations we know and put an I instead of an M. That's the entire PowerPoint, is taking stuff we know and replacing M's with I's. So for example, kinetic energy, 1/2 mv squared. I'm going to teach you all there's a rotational kinetic energy. What are we going to replace the V with? Instead of velocity, what's our rotational version? It's W, angular velocity. And instead of M, we put an I. Great. I'm going to teach you all about angular rotational kinetic energy in this PowerPoint. If something's spinning, it has it. Before you all learn about momentum, it's M times V. Later on in this PowerPoint, I'm going to teach you about angular momentum. It gets the letter L. I have no idea why, but it is. Alright, same logic as before. V gets replaced with W, M gets replaced with I. So, I'm going to teach you what moment of inertia. It's not as crazy as seems. You all actually are spared the worst of it. Each shape is going to have its own I. And you're like, oh my gosh, that sounds terrible. If I have a sphere, use the I for a sphere. If I have a cylinder, use the I for a cylinder. It's going to be very straightforward after we do a couple of these. Where does the equation come from? You are spared that. I will just tell you the equation for it. You're not going to actually have to derive I, because it involves calculus, and so you're spared. So anyhow, that's what we're going to be covering in this entire PowerPoint. We'll get through most of it today. We'll finish the rest Tuesday, and it should be good to go. All right, so we're going to find moment of inertia, how to calculate it. Newton's second law, F equals ma, upper rotation, torque equals I alpha, angular momentum, angular energy. I don't know if I checked that on here, but it'll be in here. All the things I mentioned. Okay. So I'm going to say this question out loud, and then I'm going to tell you what you need to know to answer it, and then you're going to try to answer it. I roll 4 objects down a ramp. A sphere, a solid sphere, a hollow cylinder, a solid cylinder, and a hoop. if they all have the same radius and the same mass and race from the same height, which will reach the ground first? Will the solid sphere reach the ground first, the hollow cylinder, the solid cylinder, and the hoop? Now, I haven't taught you what you need to know to answer this, so I'm going to go ahead and teach you right now. All you need is one simple concept, and it's something you're familiar with. It's something you know. You've experienced it before in your life, I'm pretty confident. So, what's easier? Is it easier for me to spin with my arms out, or is it easier to spin with my arms in? In. If you haven't experienced that after class, during class, I don't care when, spin in a circle and see what's easier. Arms out or arms in. If you've done it, if you sat in a spinning chair, you've experienced this. You know, you watched ice skaters and said maybe do it, whatever. All I've changed is where the mass is located. I didn't change the mass of my body by doing my arms out. I didn't make myself have any less mass. All I changed is where the mass is located. So the really important thing in this entire PowerPoint, kind of like the main concept, the farther the mass is from the center, the harder it is to spin the object. That's the important concept that's going to show up in this entire PowerPoint. The farther away the mass is from the center, the harder it is to make something spin. It's angular accelerate. And this is something you know. Again, just from that example I gave you. Arms out, it's harder to spin than arms in. I'll explain why later on. I'll connect it to some of the physics we've learned. But for now, that's the idea. Farther away the mass is from the center, the harder it is to spin. So using that one concept, see if you can answer this question. Sorry, just checking to make sure the stream's actually on, because I've forgotten that many times. And my shameless plug to please do the SPIs for me. I appreciate it. I forgot to send an announcement about it. I'll check it in my thing with the free response exams. All right, we'll go like 10 more seconds. There's no math here. All right, 5, 4, 3, 2, 1. All right, so the only which one's going to reach the ground first? The one that spins the easiest. The easier it spins, the quicker it goes. The quicker it goes, it makes it to the bottom first. So we got to figure out, so we're actually going to go in the opposite direction. Which of these is the hardest to spin? Which of these has the mass the farthest away from the axis of rotation? The one that is the worst, the one that has the mass farthest from the center, is the hoop. A hoop, literally the mass is all as far away as it possibly can be. All the mass is literally on the outside of it, which is as far away from the center as you can get. So, if you have a bunch of objects and you have a hoop, and they all have the same mass and the same radius, that's really, really important here. They all have the same mass and the same radius. So all this mass is really, really far. That's really hard to spin. It's really hard to spin that because it's really far away. Great. That's the worst. A hollow cylinder is just as bad. Hollow cylinder, exact same problem. All the mass is literally as far on the outside as it can be. Now, the next one's a hollow cylinder and a solid sphere. It's kind of tricky to explain this without having some. I do have some. It's really hard to, tricky to draw these. So I got a baseball, a cylinder, it's kind of uniformly kind of spread out, whereas a sphere, there's kind of like this bulge kind of on the side where the mass is like sticks out. It's actually closer to the center. So this is one of those, you're going to have to look at some spheres and look at some cylinders to prove this for yourself. A solid sphere has, out of all these options, a solid sphere has more of its mass closer to where it rotates versus a cylinder. Look at a cylinder, look at a sphere, and you kind of parse that out. But given the same radius and given all that, the sphere has more of its mass closer to the center. That's just how it is. So, this is the idea that's going to follow us through this entire PowerPoint. Nice. Good work, everyone. So, jumping to this slide, this is what I just said. In fact, maybe I should swap these slides. I don't know. The farther away you are from the axis of rotation, the harder it is to rotate. Now, this is where I get to explain why. If you'll remember, the farther away, so ignore the words it says there. We did the problem with like the two bunnies that were, one was on like the outside, one was on the inside. They're both spinning around. Which one was going faster? The bunny on the outside or the bunny on the inside? The one on the outside. The farther away you are, this bunny literally has to travel a farther distance than the one on the inside to make the same rotation the same amount of time, yada yada. Long story short, the bigger the radius, the bigger your velocity. It's hard to get things to a high velocity. It's not free. You can't just get something from 0 to 60 miles per hour for free. It's harder to go from 0 to 60 than from 0 to 20. So, the farther away you are from the center, the harder it is to make you spin, because you are literally making it go faster. You're literally making its velocity faster than something on the inside. Now, torque, you could say, but what about torque? Torque has the RF sine theta, bigger radius means more torque. And the last problem, they all had the same radius. The only reason things roll is the force of friction. They're all experiencing the same torque, so it didn't matter. And so then the final question is, okay, farther away I am, harder it is to rotate, great. How do I express that mathematically? Moment of inertia. So ignore this bottom part. This math here is very easy to prove. In fact, here, I'm actually going to do it on the last slide. How do we characterize this? Remember, kinetic energy is 1/2 mv squared. Hopefully we're cool with that. Hopefully we're cool with V equals RW. Angular to linear, multiply by R. To the power of taking this and putting it where V is, so if I just swap that in here, 1/2 m times RW squared, just swapping in that relationship. This is the equation for rotational kinetic energy, kind of, sort of. So, go ahead and make it a little prettier. I'm going to square my R. I'm going to square my W. If you all compare these two equations, if you all compare this, the kinetic energy equation, and this one, remember I told you V is like W. Hopefully we're cool with 1/2 being like 1/2. So what is M like? mr squared. Ta-da! We derived I. So, long story short, that shows up in this PowerPoint. I is mr squared for a single dot, for a single object. If you just had a point mass, we're going to talk about what those are. So here's moment of inertia. Oh, I didn't update the slides. Alright, please hold. This slide's ugly. I didn't realize I didn't grab the ones from here. So I'm going to actually start over with these ones. These are my prettier ones. I'll copy the other ones over later. Alright, boom, there's a nicer, prettier one. Apologies if I didn't upload this one. I don't know if I did for you. I had updated, but I might have forgotten to upload it. Anyway, I equals some number times mr squared. This number, this constant in the front, depends upon the object. If it's a sphere, it's 2/5. If it's a disk, it's 1/2. If it's a cylinder, it's also 1/2. I'm going to show you all a picture of like all of them together, just to set like a bunch of different shapes. If you have a point mass a point mass literally means, like, say I had a ball on a string. A point mass would be that dot on the string. We're going to do some problems, and that'll help me clarify. A point mass is any object that's, it's not the whole object that's spinning, it's like just some object that happens to be going in a circle. Literally, the next problem is going to be a point mass, and it'll help me explain that chart. So, anywho, if you have a sphere and it's rotating, I is 2/5 m r squared. You have a disk, it's 1/2. If you all go to the problem sets, literally at the top of this section is a big old list of them. On the formula sheet that I give you all in the final, I will give you all a big old list of them. If you all need to know the moment of inertia of an object, it's going to be very obvious for the most part. For example, let's just scroll through these problems and let me point this out to you. Alright, number 4, suppose you exert a force of 180 newtons tangential to a 0.28 meter radius grindstone, a solid disc. So which moment of inertia are you going to use for this? The one that says disc. Great. Looking at other problems. A father pushed a merry-go-round with a force of 250 newtons, yada, yada, yada. Consider the merry-go-round to be a uniform disc. Alright, great. Moving onwards. Assume it to be an annular ring. You're like, annular ring, what? It's the one that says annular ring. Great. Hopefully you get that. If in a problem you need to know what the shape is, I will tell you what the shape is. Oh, I guess number 8, I don't tell you, a neutron star. I assume people know a star is a sphere for that one. So, if you're unsure what shape it is, you can ask me on the test. Like, I will put it in the problem. It's a disc, it's a sphere, it's a cylinder. And then I'll give you all a big old list with all of them, and you'll be good to go. So, yeah, the rest of class is kind of applying this. Case in point, let's do this problem because I want to help you all understand what a point mass is. So a sphere means an entire sphere is rolling. A cylinder means an entire cylinder is rolling. This one, a 5 kilogram ball is attached to the end of a 2 meter string. If I spin the ball in a circle, what's the moment of inertia of the system? Assume the string is massless and the ball is a point mass. Yes, the ball is a sphere, but that sphere is not like spinning. It's not, the whole problem isn't, hey, I have a sphere that's spinning. The problem is I have a ball at the end of a string, and this whole thing is spinning. So we're going to take that ball and pretend like it's a single dot. And that single dot is spinning around. Find the moment of inertia of a single dot that's spinning around. If you look at the previous, and I'm just going to copy and paste the ones from before, and let you make the decision which one to use. Hopefully it's very obvious. And find the moment of inertia of a single dot spinning around. Some object that we just crunch into a single dot and it spins around. 15 more seconds. Once you choose the right one, the math is very simple. The only challenge here is just choosing the right equation. All right, we'll close it out in 5, 4, 3, 2, 1. Boop. All right, so hopefully it's obvious we're going to use the point mass one because it says it's a point mass. Like, that's point mass, point mass. So, anywho, I is going to equal mr squared. The reason it's mr squared and there's not some, notice that all these other numbers are a fraction that make it smaller. If your object is literally as the distance r, it's as big as the moment of inertia can be. Because it's literally all the way away from the center and it's spinning around. That's why it's mr squared. All these other ones get like some little coefficient because some of their mass is less than r. Like if you have a sphere, not all the mass is on the outside. Some of it's on the inside. And closer. So, anyway, point mass, i.e. literally an object some radius away that's going around. We're going to eventually do a problem where like you're going to have a merry-go-round and you're going to have a kid sitting on it. It's going to be two objects. You got a disk and you got a kid. So you have a disk and a point object. We'll do that one later. Anywho, so this is not a sphere spinning around. It's a thing at the end of a string. So you just 5 times 2 squared. 5 times 4 is 20. And the units are very easy. You don't even need to have them memorized. What's the unit for mass? Kilogram. What's the unit for distance? And then we square it. And that's the unit for moment of inertia. It literally comes from the math. So, and you can see all those have those units. So yay, there's the answer. All right. Cool. Here's a big old table just to show you different moments of inertia. Not only does it depend upon your shape, it also depends upon where you're rotating. So like I'm going to point out this one down here. If you had a solid disk that you're rotating like the way it rolls, we call this the principal axis. The principal axis is like the one it would roll along. It's mr squared over 2. If instead you spun that disk around like a baton, then it's a more complicated equation. mr squared over 4 plus ml squared over 12. It looks bad, but you just put the numbers in the equal sign in your calculator. So not only does it matter on the object, it matters where you're rotating. I'm going to be honest with you all, we're always basically going to be rotating through the principal axis, i.e. the way it rolls, just to keep things simple. But, you know, things can rotate all different ways. So, anyway, it's just a big table to show you there's a bunch of different moment of inertias for different objects. I equals, now if you notice, pretty much all of these are mr squared, mr squared. This one's a little funky. This one is mr squared, there just happens to be 2 r's. This one's mr squared, mr squared, mr squared. They're all mr squared with a number in front of them, basically. It's just what is that number? This one you may be like, that's not mr squared. Well, a squared plus b squared is kind of like an r squared. mr squared. Anyway, bunch of mr squareds. This one says ml squared. Well, pretend instead of l it says r. Great. Okay, so we learned about I. Let's go ahead and find I. Let's practice it. Calculate the moment of inertia of a skater given the following information. In the first step, the skater is a cylinder that has a 0.110 meter radius. Again, there's the running joke of like the spherical cow in physics. This is our cylindrical skater. It's close enough. You can approximate it. It gets us close enough. A lot of physics is making approximations that get us a sense of what it's going to be. So, in part A, the person is a cylinder. And we're going to find the moment of inertia of them. Pretend like part B doesn't exist. We'll get to it. Goodbye, part B. So, this is where, again, you would go to maybe the formula sheet or the other thing, or Google it or something. Alright. We're a cylinder. What's the equation for the moment of inertia of a cylinder? 1/2 mr squared. I do not need you all to have these memorized, so don't freak out about that. If you need it, I'll give it to you in the formula sheet. So, part A, step 2, we're solving for moment of inertia. The equation for moment of inertia is 1/2 mr squared for a cylinder. So clearly we need the mass and the R. Oh look, I gave you the mass and the R. So you just chuck them in. It's fairly straightforward. 1/2 times 60 times 0.110 squared. Most problems you're going to have to calculate I. It's going to tell you the shape, you find the right equation, you calculate what I is. Some problems they might tell you I is this number, but that's not super common. It's all about just choosing the right shape. Kilogram dot meters squared. Great. Part A done. Alright, part B. And the key to part B is, can you draw a picture of it? Now, I'll be honest, I think I forgot to include the moment of inertia for one of these pieces in the thing. But so for now, we're going to draw the picture, and then I will do for that object. Anyway, the skater with arms extended is basically a cylinder, like before. But now I have some arms, which we're going to pretend like they're cylinders. Extended, rotated about their ends. So you got two cylinders that are rotating about their ends. See if you all can draw a picture of a human where the arms are cylinders. And the arms are straight out to the side. So you got your cylinder, there's the person, and then they got arms. There they are, in all their arm goodness. They're cylinders. Okay, so how do we find the moment of inertia? You find the moment of inertia of each of those objects and you add them up. That's it. Now, something I want to point out. So we have the mass of the cylinder equals 52.5. We have the mass of the arms is 3.75. And something I just want to pause and kind of point out here. If I lift my arms, does my mass change? No. How many arms do you think this person has? We're going to assume they're an average individual. 2 arms. If you double 3.75 and you add it to 52.5, it equals 60. Just to make sure it's good. It's like, why are these numbers different? Because I've just split up the body into a few pieces. But it still equals the total. But there's 2 arms. That's important. I don't know if it's specified here. They're plural arms, so we're good. All right, we're finding I. How are we going to find I? We're going to have the I of the cylinder plus 2 times the I of the arms. I could call them rods if I want. Now, we already said what I of the cylinder is. The equation for that is 1/2 mr squared. That hasn't changed. Just our m has. Mr squared plus 2. Now, this is where I'm going to need to pop over here because sadly I didn't put this one in the other thing. The arms is not this one. So this one is about the middle, but these arms aren't rotating about the middle. We're going to use, where is it at? Actually, you all see if you can pick. There's four pictures here, 4 rods. Which one is the arms in my picture? So here's my picture. Just to clarify, the person's spinning about the middle. So I got my, which one of these four matches the arms? Is it the one about the principal axis? Is it the one about whatever you want to call this, like the middle vertical? This one's just infinitely thin around the middle, or is it this one, which is about the end of the rod? Yeah, it's the last one. The arms, if you think of my arm like a rod, that rod goes from the middle of my body, roughly, to out here. It's a little silly, but it gets the job done. We're approximating. It's good enough. All right, so this is going to be 1/3 mr squared because we chose the one about the ends. Now, this mass here is the mass of the arms. Here, the radius of the arms, mass of the person, radius of the person. So at this point, you just got to be careful to put the right numbers in the right spot. And I don't think I have any chance of fitting this in here as much as I may hope to. Right. So equals 1/2. The mass of the person here is the cylinder is not 60 anymore. It's 52.5. The radius is still the same. 1.110 squared plus 2 times 1/3 times the mass of the arms, which is 3.75, times the radius of the arms, which is 0.9. Oh, I did it. Great. And if you just plug all those numbers in, I'll let you prove this to yourself. And look, my moment of inertia is bigger. Why? Because I made the mass farther away from the center. Just like we said how we started, it's easier to spin if your arms are nearby the middle. You can see my moment of inertia is 6-7 times bigger. It is literally 6 to 7 times harder to spin the person now than when their mass is all in the inside. And this is approximately correct. I don't know. I think the numbers here are all good. I think this is reasonable. This says each arm is about 6 to 8 pounds. I think that's reasonable. 0.9 meter long arms. That might be a little from the middle. Maybe, I think that's maybe a little exaggerated. My arm's not quite 0.9 meters. Maybe it is. I don't think it is, though. It's very sad. Whatever. It's not super critical. It gets a good approximation, though. All right. And then I have a bunch of hidden slides that I would show in my calculus-based class about how to actually calculate moment of inertia and parallel axis theorem, and we ignore them. All right. So what do we do with it? The things I already told you. What do we do with it? We find angular acceleration with torque equals I alpha. It's got an I in it. We find the rotational kinetic energy by using 1/2 I omega squared. We're going to find angular momentum by multiplying I times angular velocity. That's the rest of the slide, is using I. So finding this whole what is moment of inertia, that's kind of, in my opinion, the only new thing, and I just need to teach you all how to apply it. We're going to do conservation of energy, just with a new type of energy included. We're going to do conservation of angular momentum. It's like regular conservation momentum, but we just use I's and W's instead of N's and B's. And we're going to do torque equals I alpha, which is going to be like F equals ma problems, but with torque instead. So, should hopefully go smoothly. We'll see, if you believe me. Alright, so just to test if we're cool with this whole new paint job thing, if F equals ma, and I'm going to make these super quick, because I don't want to spend a bunch of time. So I'll give like 30 seconds for each of these. What is the rotational analog for F? Instead of F, what letter do we use for rotation? Is it F, tau, P, or K? What's the rotational analog for F? All right, 15 more seconds, which is probably still more than I said. If you're not sure, take a guess. Forces make things accelerate. Whatever this is makes things angular accelerate. Alright, in 5, 4, 3, 2, 1, gone. Alright, what makes things angular accelerate? It's torque. If there is no torque, there is no angular acceleration. Why isn't it force? Just because there's a force doesn't mean you're going to rotate. If I pull on a sphere on the side, it's not going to spin. So, let's see. Yay! Great. Another freebie one. What's the rotational analog for M? Hopefully I've convinced you all of this at this point. Again, 30 seconds. We're going to be quick. This one I'm actually going to set a timer for. Is the rotational analog for M, F, I, or K? All right, 5 seconds. 4, 3, 2, 1. All right. Rotational analog for M is I. We've swapped. Hey! Now, something I want to point out that isn't really that big of a deal, but just I want you to know my suffering. Arial is the font that I use here. I think, yeah. Oh no, he's Calibri. Whatever. Calibri, Arial are two of the most accessible fonts, easiest to read because they don't have a lot of these extra things on them. Why am I mentioning this? The really, really annoying thing about Arial and Calibri is I'm going to type the letter I and the letter L. I'm not going to tell you in what order. What's the which one's the I? Fun fact, I don't remember. I is the second one. Can you tell the difference? No, one's slightly longer than the other. This is just a really annoying, this is a little pet peeve I have with Arial and Calibri. Capital I and lowercase L look literally the same. So if you're like, ooh, this one looks nice. I had to go to Times New Roman, which is not as successful, whatever. I just wanted to share my frustrations. Alright, great. Back to physics. Torque equals I alpha. I've actually mentioned this like 10 times now. Now it's on the slide. If there's a net torque, it angular accelerates. And it's something I've been saying this whole time. And now all we need to do is practice it. So there's a couple more clicker questions. So we're going to be using this now, and we're also going to be using torque equals RF sine theta. If we have a force, we're going to find the torque. Once we find the torque, we can find the angular acceleration, and yay. And if you have multiple objects all stuck together, we're just going to add up all their i's. Just like if you had multiple objects stuck together, their mass would be all their masses added together. Just like that. So, bunch of words on here that basically just say, if there's a net torque, there's going to be an angular acceleration. How much? Depends on the masses spread out. Depends on I. Just like, if there's a force, there's going to be an acceleration. How do we determine it? It depends how much mass there is. More mass, less acceleration. This is true in space as well. Just like F equals ma is true in space. In space, it is harder to rotate something if the mass is really far away from the center of rotation. Fun fact, planets are hard to rotate. They're really big. They got a lot of mass. They got a big radius. Alright, so, cool. If I apply the same torque but double the moment of inertia, what happens to the angular acceleration? You know, the classic, right? What happens to blank if I change blank? So what happens to the angular acceleration if I double the moment of inertia? Same torque. Do I quarter my angular acceleration, half my angular acceleration, double my angular acceleration, or does the angular acceleration stay the same? All right, we'll go 10 more seconds. And 5, 4, 3, 2, 1. Boop. All right, so as always, we want the relationship between these two things, three things. Torque equals I alpha. We're going to rearrange it for the thing we care about. We care about angular acceleration and how that changes. So alpha equals torque over I. So that's our original. Then we do the different one. We do the one where things are different. Torque is the same, but my moment of inertia is now double. We then pull the whatever constants to the front, and we see it's half the original. So this is if this changes, how does this change? You write the equation, rearrange it, pull out the constants, and you get it. You can also see it. This one it's really easy to think about. Intuitively easy. If I doubles, angular acceleration has to half to equal the same number. So you can do it that way. The way I just showed you though is like what if I said I made the moment of inertia 12 times bigger and the angular acceleration 3 times 1/3? It's going to be trickier to do that intuition, but if you go through this process, if I made the torque 5 times bigger, I put a 5 in front of it. If I made the moment of inertia 1/3, I put a 1/3 in front of it. And then you just pull it out and do that. Math lets us go beyond what our intuition and what we can kind of do in our head. Just like the English language lets us express ideas beyond what we could express by waving our arms around. I say that. I mean, sign language is in some ways waving your arms around. But still, it's an organized way of expressing ideas. Organized ways of expressing ideas let us discover new and exciting things and communicate things. Anyway. All right, this one I'm going to give you all a hint before we start it. Well, I'll read it first. I applied a torque of 5 newtons per meter to 2 different objects, a sphere and a cylinder. If both objects have the same mass and radius, how will the angular acceleration compare? I want to compare the angular acceleration of a sphere to a cylinder. Anytime you want to compare two things, it's a ratio. Anytime you all compare two things, you're basically building a ratio. How does this compare to this? The way we write a ratio, so if I want to compare a sphere to a cylinder, I just do a division problem. Alpha sphere over alpha cylinder equals, see if you all can build the right side, plug stuff in, get this, because this is one, maybe you can do intuitively. But building it, doing the mathematical way is going to kind of help to make sure. Do I multiply them, divide them? Which one goes on top? This tells you. Build this relationship. Once you build the right side and you simplify it, you can just multiply the alpha cylinder over, and you get in the way that we want it. So build the right side, and then after you build the right side and simplify it, multiply alpha cylinder to the other side, and you'll get it in the form that I have it. And to read the various moment of inertias for a point mass, the moment of inertia is mr squared. For a cylinder, it's 1/2 mr squared. For a sphere, it's 2/5 mr squared. And for a hoop, it's just mr squared. So, hoop and point mass, mr squared. Cylinder is 1/2 mr squared. Sphere is 2/5 mr squared. quicker than the last one, but you can do it. If you're just careful and if you can build the expression. Last hint to you is on this right side. This is alpha. Remember alpha, we found a relationship for alpha in the last problem. In terms of torque and I. So that's the equation we just found in the last slide. Alpha equals torque over I. We did that in the last slide. Alpha equals torque over I. So you can chuck that on the right side. You can actually calculate, quote unquote, the angular acceleration in terms of these things. You can't actually you don't have numbers, but. We'll go like 15 more seconds. Want to make sure we have time to solve the. There's just one problem I want to be able to go through. All right, and close it out in 5, 4, 3, 2, 1. Okay, so we just got to plug in numbers. I say numbers, equations / numbers. Then we could do something sooner. So they have the same torque. So those are going to cancel. The torque on the sphere and the torque on the cylinder is both 5. 5's on the top, 5's on the bottom, it's gone. The other thing I'm going to preemptively do is I'm going to go ahead and multiply alpha cylinder to this side. Well, no, I'll do it in steps. So alpha sphere over alpha cylinder equals 1 over, what's my moment of inertia for a sphere? 2/5 mr squared. mr squared. Divided by, what's my moment of inertia for a cylinder? 1/2 mr squared. Now, again, same thing. If you have the same stuff on the top and the bottom, what happens to the mr squareds? They also cancel. They're gone. You didn't need to know the mass. You didn't need to know the radius because they both have a share. So, we have alpha sphere over alpha cylinder equals 1 over 2/5. You just flip you just flip it. So that's 5/2 divided by 1 over 1/2. You just flip the 2 up to the top. So now it's 2. And I kind of ran out of room. Last thing is simplify this, and then we're just going to multiply alpha cylinder to the other side. So alpha sphere equals 5/4 alpha cylinder. So anytime you all have so this is one way of doing it. Works pretty well. Anytime you want to compare two things, you can just divide them by each other. If I want to say, how does this? If I say, is this 5 times bigger, 3 times bigger, 6 times bigger? You build a ratio, and you just kick the one on the bottom over. The other way I've seen people do this problem, which totally works, the torque on the sphere equals the torque on the cylinder. According to this problem, they both get a torque of 5. Great. What do you do from there? Torque equals I alpha. So I sphere times alpha sphere equals I cylinder times alpha cylinder. And you can rearrange it and also solve it that way. It works. It's the same thing, just viewed differently. So, yeah, this one's a trickier one. It's a good practice one. Oh, nice. That's better than I expected. Not because I have anything against you all, but because ratios and things like this, it's a little different than the kind we've done before. So, but what I do want to point out here is the answer. What does it say? Given the same mass, the same radius, the same torque, a sphere is going to accelerate more. And if we go back to the original problem we asked, what's going to make it to the bottom of the hill first? The cylinder. Or not the cylinder, the sphere. Why? Because it accelerates more than the other objects. Why does it accelerate more? Because it has a lower moment of inertia. So this actually connects back to the first question I asked you all today. It's another way of understanding it. Because it has a lower moment of inertia, given the same torque, it's going to accelerate faster. It's going to angular accelerate faster. It's going to spin quicker. It's going to reach a higher angular velocity quicker, to put in technically correct things. All right, big old paragraph. Don't be intimidated. Again, it's just a look. If you're like, oh my gosh, so much to the power of deleting everything. Wow, doesn't that look so much better? Do one part at a time. One part. Just because it's got 5 parts, you don't worry about parts B, C, D, whatever. Worry about part A first. So don't be scared. And this is true of anything in life. Any complex task you have, break it into small pieces and go from there. It's true of literally anything you do in life. If it feels overwhelming, break it into small pieces. You can deal with small pieces. There's the ridiculous saying, how do you eat an elephant one spoonful at a time? It makes no sense, but it gets the idea across. No one's eating elephants with spoons, but you get the idea. One small thing at a time. I have no idea where that saying came from, but I like it. All right. Father pushed a playground merry-go-round. You know, if you've ever ridden one of these, they're great. They're only slightly dangerous. They're those rides at the playground that you metal and you spin them real fast and kids fly off them and everyone has a great time. So, you got a merry-go-round. He pushes with a force of 250 newtons. Now, it doesn't specify what direction he pushes the force, but we can assume that the father is going to want to make this thing spin as fast as possible. So, if you guess that the force is this way, obviously that's unreasonable. So we're going to go with the reasonable, that he pushes 90 degrees, tries to make it accelerate as much as possible. It doesn't specify that. Probably should, but it's not a big assumption to make. All right, at the edge of the 50-kilogram merry-go-round, 1.5 meter radius, consider the merry-go-round to be a uniform disc. Tells us the shape. Calculate the angular acceleration produced when no one's on it. So, part A. We're starting with what we're actually solving for. We are solving for angular acceleration. Now, to solve for angular acceleration, we have kind of a few options. We have our angular kinematics. But to do angular kinematics, I need to know a bunch of things like angular velocity or degrees or velocity or all that stuff. The other option is what I just taught you. How do you make the distinguishment? If I mention there's a force, you're going to be doing torque. Like, that's kind of the flag there. So, just writing our givens. We got force, we got mass, we got radius. How are we going to find the angular acceleration? We're not going to use the angular kinematics equations because we literally have nothing else. I mean, if you really want, we know the initial angular velocity is 0. That is all we know. That is not enough to do angular kinematics. So we're going to have to do this whole torque stuff. So, there's an equation with an alpha in it. See if you all can figure out what equations we're going to use to solve this problem. We got some time. How are we going to solve this? So hopefully you've thought of torque equals I alpha. Why should it even accept? We're in the regime now of why do things angular accelerate? So there's a torque. Before we just said there was one, find it. Now we say why is there one? Oh, because there's a torque. Alright, is that enough? Can we solve the problem? No. We're trying to solve alpha. I, that's no problem. It's 1/2 mr squared for a disk. There are those things. Do we know the torque?
Yeah.
What is it? So this is the question, what is the torque? And there's a couple of things we want to think about here. We have to be careful. Torque, while it's a like force, it is not the same as force. So remember a torque, and this is actually coming back from the one we did last week. Torque is not the same as force. Really easy for me to prove this to you all. If the person applied a force of 250 newtons this way, away from the circle, is it going to do anything? Is it going to accelerate at all? No. Another question for you all. What if instead, so the angle matters. The angle of the force matters. What if the person applied the force in the middle? They went to the middle of the merry-go-round, somehow, some way they were able to push it. Is it going to go anywhere? Is it going to spin? No. So this is kind of a reminder that we can't just put force where torque is, because they're actually different. We have to go from force to torque, and so then the second step we got to do, torque equals RF sine theta. It's not enough to push a door to open it. It matters what direction you push the door and how far away you push the door from the hinge. It's not enough just to apply a force. You have to apply it in the right direction. And the bigger the radius, the better it is. So now it's just take these two things, smash them together. RF sine theta equals I alpha. If A equals B and B equals C, then A equals C. And I guess the last thing I can do, well, I can rearrange this. Sure, I'm going to do the quicker one. Alpha equals RF sine theta divided by I just rearranging, doing some algebra. And the last thing is, what is I for a disk? I tell you it's a disk. For a disk, I is 1/2 mr squared. I do not expect you to have that memorized. But if we go to the problem set, I for a disk, mr squared, 1/2 mr squared. It's right up there. So, I will not tell you which I to use in a problem. I'll tell you it's a disk. I'll tell you it's a sphere. I'll tell you it's a cylinder. On the final, you all will have to look at this list and choose the thing. It's not a huge step, but so it's not going to be like there's some problem in here where I say, where is it? So like in the problem set, I actually put I equals 1/2 mr squared. In the test, you're going to have to actually look and find the right one. It'll be in the formula sheet. It'll be listed. All the moment of inertia you'll need will be listed, but I'm not going to make it that obvious because I need you to know that you even need to use I. If I tell you it in the problem, it gives away too much. All right, plug in things. That's it at this point. So I'm going to chuck this over here. We're going to plug in numbers. Easy peasy. Remember the last step is just math. So 1.5 times 250. The father is going to push this thing at an angle of 90 degrees because he actually wants it to spin as much as possible. So there's my F, there's my R, it's 90 degrees. It doesn't specifically say it in the problem, but it's not a big assumption. I will tell you all on the test more specifically. Oh, we can make our life a little easier before I plug in numbers. Just to point this out. If there's an R on the top and there's an R squared on the bottom, we can cancel one out. Makes our life tiny bit easier. Anytime you can cancel things, it's good. 50 times 1.5. You plug all that in, so 250 divided by 1/2 times 50 times 1.5. Because sine of 90 is just 1. Make sure you put parentheses in your calculator. It's really easy to forget to put the parentheses on the bottom. And you get 6.67 radians per second squared. Every second, my velocity changes by 6.66 radians per second. Cool. So this is kind of our first time using this. Torque equals I alpha, torque equals RF sine theta. Yeah, if you want to make the analogy. Yeah. For the angle? Yeah, you could, if you really want, pi over 2. As long as you put the angle here is 90 degrees, so a perpendicular, it spits out the same. So this sine of theta, you can do it in degrees, or you can do it in radians. It doesn't matter. Whatever you prefer. The only time we got to be careful with the angle stuff is when we're actually using the angle in like multiplication and addition. When you plug it into sine, cosine, tangent, you can choose whatever you prefer. That's a good question. Yeah, whenever y'all are working with sine, cosine, tangent, you can choose degrees or radians. Pick your poison. When you all are doing angular kinematic stuff, you better be in radians. I mean, not even in radians mode in your calculator, but just make sure you're not plugging in degrees into those angular kinematics equations. Because you're literally adding numbers together, whereas this is the magic of sine and cosine. Alright, so, part B. What about if there's an 18 kilogram child sitting 1.25 meters away from the center? Find the angular acceleration. So, I really like this problem because it basically shows the skills, all the skills that I need you all to know. So, part B, I'm going to copy all this stuff and chuck it over there. Part B, we need to draw a new picture. If you don't draw a picture, it's kind of tricky to understand what's different about this problem. So part A, a disc that a father pushes. That was part A. Draw the picture for part B. In fact, I'm going to get you started. There's still a disc. The merry-go-round ride has not disappeared. What's new in part B? So, there's part A. Here's part B. I want you all to try to draw what's new in the picture based on that. Based on the word here. It says an 18 kilogram child sits 1.25 meters away from the center. Alright, for the sake of time, here's my new picture. There's a kid sitting on it. That kid is a dot. We're going to pretend like that kid's a dot. Anytime we put something on something else, we're just going to pretend like that's a dot. The father still pushes with a force. So what's different in this problem? It is the exact same process. There's only one thing that changes. So to understand what changes... Great, I can actually do this in class. I push a desk with some force, and it accelerates. I now put my backpack on the desk, and I push the desk with the same force. Find its new acceleration. What changed when I put my backpack on the desk? The mass. What's our analogous thing to mass? What's our new thing? I. It's the same problem, but your I has changed. You have the original I, now you have more. Your I is now bigger, so this problem is the exact same one. We're going to solve for alpha. I got to make my big old list of given. I'm going to keep the force up there. I'm going to now clarify these are the disk, radius of disk, radius of disk. I now have the mass of a child, which is 18 kilograms. And I have the radius where the child's located, which is 1.25 meters. It is the exact same equation, RF sine theta equals I alpha. The only thing that's new is I have I of the disk plus I of the child. Just like if you all were doing force problems, if the mass change, if you have two masses, you add them together. I have two objects, add their I's together. So, RF sine theta. This R here is of the disk because that's where he's pushing it. For the disk, it's 1/2 mr squared. That hasn't changed. Nothing new. For the child, he's a point mass. So he gets that mr squared. Remember that first problem we did of a ball on a string and it was mr squared? If you have a dot on an object, it's a point mass. That's the kind of thing that we pretend like this child is just a single blob. That blob we call a point mass, and that point mass spins around and it has a moment of inertia of mr squared. And then you just solve for alpha. It might look gross, but it's the exact same thing we just did. You just got an extra I term in there now. So, to plug in the numbers, so step 4, the radius of the disk is 1.5 times 250 times sine of 90, just like before, equals 1/2 times 50 times the radius of the disk, 1.5 squared, plus the mass of the kid, which is 18, times the distance that the kid's located, 1.25 squared, times alpha. Solve for that whole blob on the left, solve for that whole blob on the right. So 1.5 times 250, that's 375, equals the whole blob on the right, 0.5 times 50 times 1.5 squared, plus 18 times 1.25 squared equals 84.375 times alpha. If you divide those, you get that alpha equals 4.44, I think. That's the answer. I know this looks worse than it's just adding another I. Just like when we did a force problem, if you had two objects, you just added their masses together. It's the same logic, it just looks worse, but it's the same thing. You just add the I of the kid. If there was 2 kids, then you'd have another I for the other kid, and you would just add that to it. 5 kids, add them on up. Fun fact, if the kid was sitting in the middle, it would change absolutely nothing. If the kid was in the middle, then the kid's radius would be 0, and it wouldn't change the moment of inertia at all. So, that's just kind of to prove some ideas. Yeah?
If the kid was sitting on the opposite side, that wouldn't, from
Yeah.
the center, it wouldn't make it negative.
Yeah, that's a great question. If he's on the other side, it doesn't matter. R here is just how far away you are
Okay.
from the axis of rotation. Yeah, great question. Doesn't matter. Because at some point he's going to end up over there.
Right.
Doesn't change anything. Yeah, great question. So anyway, this is the new step. We're just going to keep practicing finding I in new contexts and using it in these various contexts. I can almost guarantee we're going to finish on Tuesday, y'all. And then Thursday will be review. So we are on track. There is 13 more slides. All right. What's up?